All right, this is the last practice test video where we're going to write condensed electron configurations for each of the following elements, and it gives us some examples here. I have a periodic table here that'll help us, periodic table here that'll help us, and then I added some additional questions that might show up on the test about paired and unpaired electrons, half-filled orbitals, excited electrons, and some other crazy wordage that might show up as well. So first we have potassium. So looking on here, we can find that potassium is in group or period 4. The preceding noble gas is argon, and so we'd put argon into brackets. And then we'd find the 4th energy level, so you'd write a 4, and then you'd put an S right here, because remember this is the S filling area, and we'd have 1 electron there, so we'd put 1 superscript of 1. So argon 4s1, that would be potassium. The second one is selenium. Selenium right here is in the 4th energy level once again. Preceding noble gas would be argon, so once again we'd start with argon, and then we'd go 4s2, and then we'd have the 3ds all filled, and there's 10 of them right there, so it'd be 3d10. And remember that the d orbitals are 1 energy level less than the principal quantum number right here, then n equals 4, so that'd be 3d10. And then we'd have 1, 2, 3, 4 for the p orbitals right here, so we'd write 4p4. If we were writing the orbital notation for this, we'd put 1 box or one line right here for the s's. We'd have to put 5 lines or 5 boxes for the d's and 1 electron in each orbital before they start to pair up, for a total of 10 for the 3 d's right here. And then the 4 p's, we'd have to have 3 orbitals or 3 lines or 3 boxes, and we'd put 1 electron in each box before they start to pair up, so we'd have 3 electrons in there, and then we'd pair 1 of them up. So in the end, I'd have 2 unpaired electrons then in the electron configuration of selenium, these 2 right here. I'd have lots of paired sets of electrons right here, and all of them, of course, that are in the argon core electrons. I'd have this set of orbitals with these 2 half-filled orbitals, I guess you'd say. The sublevel would be one more than half filled, because the sublevel, of course, contains 3 orbitals. And I would have no excited electrons, because they'd all be in their what's called their ground state, because there's no promoted electrons from where they would normally be. Chlorine, my next one, is right here, and the preceding noble gas from chlorine, looking backwards this way, would be neon. And so we'd write down Ne and put that in brackets, and then we'd go from there, and it would go to 3s2, 3p5. So 3s2, 3p5, or you could just write it 3s2p5. If you didn't repeat the 3, that's okay, as long as you had a total of 7 electrons right here, and the neon as the core electrons. The next 2 are kind of tricky because they're actually ions. We have nickel plus 3 in here. And this one is extremely tricky, so I'm going to save it for last. But then we have oxygen minus 2. So oxygen right here normally has 8 electrons, but since it's minus 2, that means that there are 2 additional electrons added to that oxygen. So instead of having 8 electrons, it now doesn't have 8, it has 9, it has 10 electrons. And so it would actually have the noble gas configuration of neon, and so some tricky student would just write down Ne, because it's a noble gas core electron configuration, and they'd be right. But if you wanted to write it just as oxygen was, you'd write down helium first, He, and then you'd write 2s2, and then p6, because 1, 2, 3, 4, 5, 6 would fill us up to where oxygen with a minus 2 configuration would be. The last one is, and then, by the way, if we were writing the paired and unpaired and filled orbitals, for the p electrons right here, we'd put 1 in each orbit, and then we'd pair them up like this. And then for the s, we'd have 2 paired like this, so we'd have in the outer, well, I guess there's not really an outer shell because it is neon, so the outer shell are the s and the p orbitals. We'd have 4 completely filled paired electron orbitals. All right, the last one is nickel, and I'm just going to fill a new page with that. It's Ni positive 3, And nickel, of course, on the periodic table is right here and has 28 total electrons. And if we look back from it, its nearest noble gas would be argon. So here's nickel, and then we'd back it up and we'd go to argon right here. And so we'd put argon as its starting. Then in a normal nickel, we'd write 4s2. And then I'll do the orbital notation like this. And then we'd go 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8 in the D. And remember, that'd be a set of 3 D orbitals. And so that would have 5 blanks or 5 boxes. And we'd go 1 in each box, and then you'd start to pair them up. So 1, 2, 3, 4, 5, 6, 7, 8. So that would be nickel in its normal state, not the +3 state. But now since it's +3, that means it lost 3 electrons, because when you minus a -1 thing, remember electrons are -1, you now become positive, and so it loses 3 electrons. Now the electrons that something loses are always the S and the P electrons from the highest energy level. Those are the ones that it loses first. If there are no more electrons in that highest energy level, you don't go into the core electrons, then you have to take them from the D orbitals. And so the highest energy level electrons for nickel are these 4 S's, because 4 is higher than 3. And since we are +3, we'll take both of those away, and so we'd actually end up with an electron configuration of argon, 4s0, you wouldn't have to write the 0, you wouldn't have to write 4s at all because there'd be none of those. And then we need to get rid of 1 more electron as well. And you'd take 1 electron from one of these paired sets right here. You wouldn't take one that's out here. Take 1 away from right here, and so you'd get rid of 1 of these 3D electrons, so you'd end up with 3d7 then instead of 3d8, and so then you'd have an empty orbital right here, and then in the 3D orbitals you'd end up with 2 of them that are paired, and then 3 that have unpaired electrons in them as well. 3 unpaired electrons in that Ni+3 electron configuration.